This video provides an introduction to nuclear magnetic resonance spectroscopy, which we will call NMR spectroscopy. NMR spectroscopy is similar and different to the other two types of absorption spectroscopies that we will study here, which are infrared and UV-Vis. Right? The motions that are excited during nuclear magnetic resonance spectroscopy is the nuclear spin. So that's where we start trying to define what the nuclear spin is. Now, spin is a fundamental property of matter, and we have already talked about spin when we were looking at the electronic structure of atoms and molecules, when we're talking about the electronic spin. Okay, so now going back to the simplest atom that we can think of, the hydrogen atom. Okay, the hydrogen atom has a nucleus with a proton, and then an electron in the periphery, which we have learned the behavior of using quantum mechanics. And again, we said that this electron can have spin, an electric spin, and there's no classical analog to that spin in motion, but the way that we understand it is that that spin can either be in one direction or in another direction, and we call it clockwise, counterclockwise, up or down. And again, it's not easy to explain exactly how that spin in motion is, because there's no classical analog, it's just a quantum property. Now that's electronic spin, but that's not what NMR spectroscopy plays with. Instead, NMR spectroscopy plays with the nuclear spin. Right? So we forget about the electron for just a little bit, and then we focus on the nucleus, and it turns out that the nucleus can also spin about itself. Okay, so there are some rules that tell you what atoms in the periodic table can have a net spin. Okay, so that's kind of sort of a gross selection rule for NMR spectroscopy. The rule is that you need to have an odd number of neutrons, an odd number of protons, or both. If you satisfy those rules, then you have a net spin, and then you can carry out NMR spectroscopy. Right. So going through the periodic table, we can start to look at various isotopes. For example, proton, which is the first atom in the periodic table, the first isotope that we can talk about, has one proton, which is an odd number of protons, which means that this atom will be NMR active. Okay, so we will be able to do NMR spectroscopy with the proton, okay, the hydrogen nucleus. Now, as we go through the periodic table, we can stop, for example, in one of the atoms that is more important to the life sciences, which will be carbon. Okay, and the most abundant isotope of carbon will be C12-6. Okay, a nucleus that has 6 protons and 6 neutrons. Notice that carbon has an even number of protons and even number of neutrons. Okay, so it does not satisfy that gross selection rule. That means that this nucleus will not be NMR active. Okay, now this is not the only natural isotope that we have of carbon. It turns out that there's a C13 isotope which has about a 1% more or less abundance in nature, and this in this case this atom will be, or this nucleus will be, NMR active because you have an odd number of neutrons. Okay, 7 neutrons, 6 protons. So that satisfies that gross selection rule, and then C13 will be NMR active. So there are other nucleus in the periodic table that we can go through, but the ones that we're going to be interested in are going to be these ones. Okay, fluorine-19 is going to be interesting to us, and then phosphorus-31. All right. So again, there's many isotopes in nature that satisfy, that are NMR active. Okay, but the ones that we're going to be concerned with in this material are going to be these 4, which will be sufficient. Okay, all of them are NMR active, and they also belong to a class that has something that we call a total nuclear spin of I is equal to 1/2. Okay, now this is important because nuclei that belong to that class only have 2 spin-in motions, much as an electron. Okay, the spin-in motion that is going to be one way, and the spin-in motion that is going to be a different way. Okay, 2 spin-in motions, clockwise, counterclockwise, up and down. Again, we use these simple ways to describe the spin-in motion about itself. Okay, again, using simple models like up and down or clockwise, counterclockwise, even though in reality the spin-in motion is quantum. That means that it's actually very hard to visualize. Okay, right. So. Again, the rest of this chapter on NMR spectroscopy is going to be invested in trying to see how nuclei, like these ones, that are NMR active and have a total spin of 1/2, how they behave, and how you can do actually NMR spectroscopy with them.